Hello, I welcome you all to your own channel MSK Learnium. In this video, we are going to discuss about the composite section, that is analysis of bar of a composite section. So analysis of bar of a composite section, before that we need to know that what is the composite section is that. So composite section is nothing but any section which is made up of the more than one material. That section or that body we call it as a composite section or composite body. So let's say that example is that any component is there which is made up of the two different material, let's say steel and copper, or you can say the wood and concrete, right, iron and the concrete. So these all are the example of the composite section. So suppose you have a pillar is there, right, that is column or beam. So if you look at that, what are the material we use to design the column or a beam, that is the concrete, the rod, is it or not? So these are the combination of different materials. So that combination different material, more than one material is involved, so that section we call it as a composite section. So in this, what we have to do, that when we have a composite section is given, right, so what stresses can be induced in each material, that we need to know. Suppose one section is made up of the steel and bar, right, so the steel and the total load is act on the section. So what will be the load shared by the steel and what will be the load shared by the copper, that we need to find, right. So for that what we will do, that we try to draw one composite section figure. So first of all, you will draw that, or you can write first what is the composite section. So composite section nothing but you can write the composite section is one which is made up of more than one material, right, more than one material, right, one material. That, like say you can say the example is the any section which is made up of the steel and copper, right, iron and steel. So these are the example of a composite section. So now we have to do the analysis of a composite section. For doing the analysis of the composite section, what we will do, we'll draw one composite section body, right. So here you have a one section I am making, right. So let's say the two rod is there, or two section is there which is of different material, right. So this is one and this is the another one, okay. So this is the another one. Let's hatch them. So it signifies that this body is a solid actually, right. So in your engineering graphics you know these things. So now we can hatching this and this also, right. So now let's say these body are like this is hinged, right now, and the load is acting, the total load is applied on the body is, let's say it is the P, right, and this is fixed at the one end, right, and hinged at the another end, right. Now you can say this is one section 1 and this is the section 2. It is made up of something and it is made up of the something, right. Now what will happen, that first of all you need to consider that this material, this section is having Young's modulus is something else and this Young's modulus is something else, right. So in analysis of composite section, only two things you have to remember, that extension in this element and the extension in this element will be same, right, and the load shared by the two body or the two section will be equal to the total load, right. So these condition we have to satisfy for the composite section. So first of all, what we can say, that you can make a point that for composite section, or composite bar, you can say for composite section or composite bar, extension extension or compression. It's not like that ki always extension. It's depend on the nature of the load, as we have discussed in the previous class, right? So if it is the pulling, it will be extension. If you push, it will be the compression. For composite section, extension or compression, extension or compression in each bar is equal, right? Is equal. Means extension will equal means what? That means you can say deformation per unit length will be same, right? That you can say the hence deformation per unit length is same. Deformation per unit length is same. Means what? That is strain in each bar is equal. Strain in each bar is equal, right? Strain in each bar is equal, right? So this is the one condition. Second is what? The second is nothing but this total load P is equal to the load shared by the bar 1 and the load shared by the bar 2, their summation. So next point you can make that see here that the total external load right on the composite section, on the composite bar is equal to the load carried by each different material, is equal to load carried by each different material, okay, each different material. So this is the condition you have to satisfy, that total external load on the composite bar is equal to the load carried by each different material. So these two conditions we will satisfy and we will do the analysis of a bar of a composite section, right? So before that, whatever the section we have considered, let's say this is the bar 1 and this is the bar 2, right? So this bar 1 is having load is P1, load is P2, Young's modulus is E1, Young's modulus is E2, cross sectional area of bar 1 is A1 and the cross sectional area of bar is A2, right? Stress induced in bar 1 is sigma 1 and stress induced in bar 2 is sigma 2. So very quickly we can write down this data, right? Why? Because while you prepare it will be good, right? So you can easily understand at the time of revision. So now you can say let P is equal to total load, P is equal to total load on composite bar, total load on composite bar, right? And that L is equal to length of composite bar, length of composite bar. In the sense L1 and L2 will be the length of bar 1 and length of bar 2, right? A1 is the cross sectional area of bar 1, right? And A2 is the cross sectional area of bar 2, right? Then you have a Young's modulus, that E1 is equal to Young's modulus of bar element 1, right, of bar 1, and the E2 is Young's modulus of bar 2, right? Then you have a P1 is the load shared by bar 1, you can say P1 is the load shared by bar 1, right? And the P2 is equal to load shared by bar 2, right? Similarly, that sigma 1 is the stress induced in bar 1, stress induced in bar 1, and sigma 2 is equal to stress induced in bar 2. So these are the nomenclature we have taken into the consideration, right? Next, what we need to do, as we have satisfied the two condition, we have to satisfy the two condition. First is what? For composite section, extension or compression in each bar is equal, and hence the deformation per unit length. Deformation per unit length is nothing but the delta L by L, which is the strain in each bar is equal. And second is the total external load on the composite bar is equal to the load carried by each different material, right? So first of all, what I'll do that, first of all I will say that a strain in each, that is load carried by the total load carried by the composite section equal to sum of the load of each bar, right? So first condition, you can say P is equal to P1 plus P2, right? Let's say this is equation 1. Now we can see the what is P and what is that. So sigma 1, that is stress in bar 1, is equal to what? Sigma 1 is equal to P1 by A1, which give you the P1 is equal to what? Sigma 1 times of A1. Similarly, sigma 2 is equal to P2 by A2, which gives you the P2 is equal to sigma 2 times of A2. When you substitute these value P1 and P2 in this equation, that equation will be in this form, that P is equal to sigma 1 A1 plus sigma 2 A2. By using this, you can calculate the stresses in each bar or the load also. If the load is not given, you can calculate the total load on the composite bar, okay? And if the load is not given in that different bars, so you can calculate by using this. Second condition is what? The deformation per unit length is equal, that is a strain in bar 1 is equal to a strain in bar 2. So second condition, you can say that a strain in bar 1 is equal to a strain in bar 2, right? That is a strain is equal to what? Let's say that is E1 is equal to E2, and strain is equal to what? In from the Hooke's law, stress by Young's modulus, right now. So previously we already discussed these things. So a stress sigma 1 by E1 is equal to sigma 2 by E2, right? So on behalf of that, you can say that you'll get the relation between sigma 1 and sigma 2, and then you can substitute into this equation, you'll get that answer, right? So here you can do like this, that is, let's say sigma 1 is equal to what? That sigma 1 is nothing but the E1 by E2 times of sigma 2. That one relation you will get in terms of the sigma 1 and sigma 2. When you substitute this equation, this value into this equation, you'll get the single form equation, right? And then you can simplify. So here you can see the modulus of elasticity, that Young's ratio of Young's modulus we have taken. So these ratio is also known as the modular ratios, right? So this is what the analysis of a composite section, right? So only whenever the composite section problem will do, you need to satisfy two conditions. The total load is equal to sum of the two loads, and the strain in each bar will be equal, and then you can generate and get that answer simply. Next, we can say that modular ratio, right, which we have discussed just now, that sigma 2 is equal to sigma 1 is equal to E1 by E2 times of sigma 2. So here you can write that is modular ratio, right? In short answer you can get in your university exam and in SSC, JEE, TS, Genco and all those, where you can get these type of questions, right? So modular ratio is what? The ratio of E1 by E2 is called the modular ratio. So you can define the ratio of E1 is the Young's modulus of bar 1, and by E2, Young's modulus of bar 2. The ratio of E1 by E2 is called the modular ratio, right? Modular ratio of first material right, of first material to the second, right. So modular ratio is what? That modular ratio mathematical equation you can see, modular ratio is equal to E1 by E2, right. So this is the modular ratio formula, you always remember that ratio of the two Young's modulus is known as the modular ratio, right. So whatever we have discussed, that we did the analysis of a composite section, regarding to that we'll do one worked example, right. That problem we will solve and then the things will be very clear to you, right. So write down that question. We are going to solve one numerical problem. The problem is on the screen, please. That two vertical rod, one of steel and the other of copper, are each rigidly fixed at the top and 50 centimeter apart. Diameter and length of each rod are 2 centimeter and 4 meter respectively. A cross bar fixed to the rod at the lower end carries a load of 5000 Newton such that a crossbar fixed to the rod at the lower end carries a load of 5000 Newton such that the crossbar remains horizontal even after loading. Find the stress in each rod and the position of the load on the bar. Take Young's modulus for steel is 2 into 10 to the power 5 Newton per mm square and for copper is 1 into 10 to the power 5 Newton per mm square. So what is that question? The question is, we have a one composite section and that section is made up of steel and copper, right. So the diameter of the steel and copper is 2 centimeter, right, that is 20 mm, and the length of this rod of steel and the copper is 4 meter, that is length is same, and these two rods are separated by certain distance. That distance is, suppose this my hand right now, so these two, one is the steel and one is the copper, so these two are separated by 50 centimeter distance, right. Then which is fixed at the bottom, right. At the lower end it carries a rod and that rod is having load is what? 5000 Newton, right, and the load is situated at certain distance. That distance we can say this is the, that a load is carried at a distance of x from the you can say any material, right, and then you have to find out the load stress in each rod and the position of the load on the bar. So we have a question. First of all, whatever the problem is given, we try to draw this figure and then we'll understand the problem. So problem is that, suppose you have a two bar is given, right, that is a steel and a copper. So this is the top portion, let's say this is your steel rod, right, and this is the copper rod, right, this is the steel and this is the copper, and these are at the lower end it is connected, fixed, right, and here the load is acting which is 5000 Newton. This load is 5000 Newton and the load is act at a distance of x, right now it is at a distance of x from the copper. This is the copper. On the right side you have a copper and on left side you have a steel, right. So and these two rods are separated by a distance of 50 centimeter, right, and the area diameter of these two rods are 2 centimeter and the length is 4 meter, right, the length is 4 meter. So as the length is 4 meter, so you can say here that this length is the 4 meter, right, this length is the 4 meter. Now what we need to do, that first of all we have to satisfy the condition for composite section, means two condition you need to satisfy. The total load 5000 load is equal to loading this plus loading this one, and then we have to say the strain in steel is equal to strain in copper. So first of all, before that we need to find out the cross sectional area of a steel and the cross sectional area of the copper, right. So write down, this the figure is given, right, that is the load is given at a x distance from the copper, so you have to find out the position of the rod also, right. So now we can say given data given data, right? That is diameter of a steel, ds is the diameter of a steel and dc is the diameter of copper. Both are same, which is 2 centimeter, right? And this is nothing but the 20 millimeter, right? So here itself we can calculate the area. Diameter is same, so area will be same. So as is equal to ac, that is equal to pi by 4 ds square, right? Any d you can say, ds or dc. So this is the pi by 4 into 20 square, right? So on simplification you will get this values, that is 100 pi. Let's take the in terms of pi only. This is the mm square, right? So area of steel is equal to area of copper. Why? Because it is diameter of the steel and copper are equal, right? Next you have a given, that is the Young's modulus for steel and Young's modulus for copper, right? So let us imagine that Young's modulus for steel is nothing but the ES is equal to what? 2 into 10 to the power of 5 Newton per mm square, and Young's modulus for copper is EC is equal to 1 into 10 to the power of 5 Newton per mm square. Okay. Next, the total load on the composite section or of composite bar is 5000 Newton, which is P, right? So now take out the question. So now you can say the total load on composite section, that P is equal to 5000 Newton, right? 5000 Newton. And the length of steel and the length of copper is 4 meter. This is 4 meter. So you can say the length of steel is equal to length of copper, means LS is equal to LC is equal to 4 meter, right? Then all the things we have written. Now what we need to do, that we can satisfy the conditions, right? So first of all, what I am doing, that I am writing the first condition, that total load P is equal to P1 plus P2. Sorry, that in terms of S, that is load on a steel plus load on copper. You can take 1 and 2 also, no problem, but the given data we took as a S and C, that is a steel and copper, so we need to write it here, otherwise it's create confusion, right? So the total load on the section is equal to load shared by a steel plus load shared by copper. If I want to change this in terms of the stress, so total load is equal to what? Stress into area, that is sigma S into AS plus sigma C into AC. Let's consider this equation 1, right? So we will leave it as it is. Okay, that load is equal to 5000, right? Next is what? That we can say the strain in steel is equal to strain in what? Strain in copper, right? So strain in steel is what? That is ES is equal to EC, and a strain is what? That strain is nothing but the, from the Hooke's law, sigma S by ES is equal to sigma C by EC. You cross multiply, you will get the relation between S and C, right? So I can write here that sigma S is equal to ES by EC into sigma C. Okay, now so sigma S is equal to what? That is stress in steel is equal to Young's modulus in steel is 2 into 10 to the power 5 by 1 into 10 to the power 5 into sigma C. This 10 to the power 5, 10 to the power 5 get cancelled. So stress in steel is equal to, we can say, 2 times of stress in copper. This relation we created, means we generate one relation that will be helpful while we substitute this value into this equation. We'll get the single term equation, right? Now then you can say from here that substitute the sigma S into the equation 1, right? So we can say substitute sigma S val in equation 1, right? In equation 1. So what is equation 1? That P is equal to 5000 I am taking this 5000. P is equal to, I'll show you here that equation is this one. P is equal to sigma S AS plus sigma C AC, where P is nothing but the 5000. So directly I am substituting P is equal to 5000 is equal to sigma S into AS. So sigma S is what? That sigma S is nothing but the 2 times of sigma C, and the AS is equal to 100 pi, right, plus sigma C into AC. That is, you can say sigma C into 100 pi, right? So 2 sigma C 100 pi and 100 sigma C 100 pi. That means 300 pi sigma C, right? So you can say 5000 is equal to 300 pi times of sigma C, right? That means the sigma, this is the equation what we have converted this equation into single term. If before that it was in double terms, right? That is sigma S and sigma C was there right now. So now that to get the solution is quite easy, that sigma C is equal to 5000, right, by 300 times of pi. Let me check the answer. So your answer is 5000 300 pi. Yes, 5000 by, it is correct, sigma C we got right now. Okay, so sigma C we got, that is sigma C is equal to 5 point how much 305, and that area we have taken in terms of the millimeter square, right? Let me check once. Yes, millimeter square. So this will be the Newton per mm square. The stress in a copper bar is the 5.305 you got right now, that is Newton per mm square. When we substitute this sigma C into this equation, we'll get the sigma S. So sigma S is what? Simply twice, that is 10.60, right? So you can say further, next, yes, so next you can say this, that is sigma S is equal to what? That is sigma S is equal to 2 times of sigma C, that is 2 into 5.305, which is nothing but answer into 2. So 10.61, right? So the stress in steel is nothing but the 10.61 Newton per mm square, right? So the question is that we have to find out the load share in the steel and copper, right? So stress in steel we got. So load in steel is equal to what? Load in steel is equal to sigma S into AS, that is 10.61 into 100 pi, right? We'll get the PS, okay? And similarly PC also you can calculate. So this is 10.61 answer into 10.61 answer into 100 pi. So that is your 191.63. Is it correct? But this load is very 5200 plus 2 plus 10, right? Sorry, 10, yes, 10.61 into 100 pi. I took the wrong values. Just hold down. So your answer is yes. So now 4 times 3.33 means 3333.33 Newton the load on the steel. This much load is shared by the steel, or you can say carried by the steel, right? So now you can say load carried by the copper, that PC is equal to sigma C into AC. So sigma c is what? 5.306, right now. So you can say 5.306 into 100 pi. Okay, so here you can write 5.306 into 100 pi, which is your 1666.66 Newton. This is the load shared or load carried by the copper. So one answer we got, that is what? Stress in steel and load in steel and load in copper. Now we have to find out that the load is at 5000 Newton at the lower end, which is at a distance of x from the copper rod, right? So you have to find out the position of a load at which it is acting from the copper, right? Or you can say from the steel also. So this position, it is a specified x. So x value you have to find out, right? When the load is acting 5000, so despite of this load, these two, that is rod, steel rod and copper rod, is not deviating, means it is in the stable in the position, right? So at what distance it is acting so that the steel rod and the copper rod is it in the stable condition. So for that, whenever you have to find out the position, it means that we can take the moment. So what I'll do, I'll take the moment about the copper. So moment about the copper means what? These two forces will consider, that is 5000 Newton, the load, total load by this composite section, and the load carried by the steel, right? So moment is what? Force into perpendicular distance, means 5000 into x is equal to load of a steel into 50 centimeter, right? So the answer you will get in terms of the centimeter only, right? Now to get the position, second is what? Position of the load, right? So second question, you have a position of load, right? Load is what? Position of load 5000 Newton, that is x you have to find. X is equal to what? So for that we can say take moment about copper rod, right? Taking moment about, or take moment about copper rod. So when you take moment about copper rod means what? The total load P into x is equal to load on a steel into that separation between the two rods. The two rods are separated by a distance of 50 centimeter, right? Into 50. So we can simply get x is equal to what? Load carried by a steel is, just now we have calculated 3333.33. So this is the 3333.33 into 50 by total load is what? 5000, right? So this position you calculated. So let's do that. That simply 4 times 3.33 into 50 by 5000. So your x is 33.33 centimeter from the copper rod. So the load 5000 is acting, means applied at a distance of 33.33 centimeter from the copper rod, right? So this is what we can do the analysis of a given composite section. This type of problem is very easy, right? So whenever the composite section problem will come, you will apply the two methods, that load shared, total load is equal to load shared by each rod, and the deformation per unit length in each bar is equal, that is the strain in each element is equal, right? So in next video we will see the thermal stress analysis in composite section. Thank you.